All right, so we have looked in the past at taking derivatives of trig functions. We have looked at some integrals of trig functions, really just sine and cosine, or ones that are set up really nicely. Like if they ask you for the integral of secant squared, we know that that is tangent because the derivative of tangent secant squared. All right, but what if we just needed the integral of secant, or just the integral of tangent, or something like that? How are we going to work with that? Okay, well, tangent and cotangent are actually not too hard to derive. The secant and cosecant take a little bit of trickery that we'll look at here. We're going to do tangent and secant. Cotangent and cosecant are very, very similar, so we're not going to actually do that all the way. But well, let's look at tangent first of all. If I were trying to find the integral of tangent, the first thing that I would do is, after realizing I don't really have a rule for this yet, and I'm kind of stuck, the thing that I would think of next is, well, what about some identities? All right, and the identity, we know that that tangent equals what?
Sine over cosine.
Yeah, sine over cosine. Okay, and now that we see a rational function here, that should cause us to think, okay, well, if I have a rational function, is that u prime over u? Okay, is it u prime over u? Well, let's think about this. U would be cosine, all right? That would be cosine of x. What is the derivative of cosine?
Negative sine.
It's negative sine, okay? So negative sine of x is what I would need in the numerator. Do I have that?
Yeah.
It's close. What?
You just put the negative before the
Okay, yeah. I'm going to put a negative in here so I have u prime over u, but to counter that I have to put a negative out in front of the integral as well. Okay? So, now that I have the integral of u prime over u, we can use our rules and write this as negative ln of the absolute value of u. And u happens to be cosine of x. All right? So this is negative ln of the absolute value of cosine of x plus c. All right? So we just derived the integral of tangent. Okay? And of course, cotangent could be done very similarly. All right? Cotangent x is cosine over sine. Alright, so if I'm taking the integral of cotangent of x dx, I'm taking the integral of cosine over sine dx, and if sine is u, the derivative of sine is cosine, so I actually don't have to do anything to this one, and it's just ln of the absolute value of sine of x plus c. Okay? So now we have two more rules. One for tangent and one for cotangent. Okay? So that moves us on to secant. All right, secant. And you actually, if you look down here, you can see we have all these rules, which, by the way, you should memorize. Okay? In fact, I would recommend either looking up a Quizlet or creating your own for all the integral and derivative rules that you need to know for the exam. Okay? And if you find a good one that has them all, maybe look for one that was made by a teacher. If you find one and you want to share it with everyone, that would be great as well. Okay? But so you see here, the integral of secant is the natural log of absolute value of secant plus tangent plus c. Okay, so you wonder, how in the world do we get this? Well, this is the one that takes a little bit of trick, if you will. What we're going to do here is we're actually going to take the integral of secant, and I'm actually going to multiply by a form of 1. You say, well, why? Well, because I know it works, okay? Somebody else figured out that this would work, and it does work, so we'll go with it, okay? I don't know what made someone think to try this originally, but this is the kind of thing that, you know, this is how these rules come about. They're trying to look for some way to come up with an integral rule that uses things that they already know, and so somebody tried this. Alright, so what we do here is we're actually going to multiply by the form of 1 secant x plus tangent x over itself. We know secants and tangents kind of pair together well because they have, with the derivatives and integrals and even with the Pythagorean identities, okay? So what we'll do here is we'll actually go ahead and do the multiplication, and this gives us secant squared x plus secant times tangent all over secant plus tangent. Okay? Now that we see a rational function, one thought might be, oh, if I split that into two separate fractions, I could reduce them. I could try to reduce them, but then you kind of undo everything you just did. Alright, so that's not going to be helpful. So then we think, okay, well, it's a rational function. Maybe it's u prime over u. Okay, well, let's see. U is going to be secant x plus tangent. So u prime, what's the derivative of secant? Secant times tangent. And what's the derivative of tangent? Secant squared. Okay? So now we notice that that actually matches what's in our numerator right now. Okay? It matches what's in the numerator. So we actually do have u prime over u. Yeah. And so now we know that the integral of this is the natural log of the absolute value of that denominator, u. So it's ln of the absolute value of secant x plus tangent x plus c. Okay? You can probably tell that if we wanted to find what the derivative or the integral of cosecant is, we could use a similar process using cosecant and cotangent. All right? And that's how we would get the rule you see down here. The integral of cosecant's negative ln of cosecant plus cotangent, absolute value. Okay? All right, so let's look at a couple examples of how to use this, and then we'll be done with this. So we have the integral from 0 to pi over 4 of the square root of 1 plus tangent squared x dx. So the first thing you might think of is you see that 1 plus tangent squared inside the square root. What's the first thing that might come to mind there?
1/2. We put it to 1/2 power.
Okay, maybe put it to the 1/2 power. Okay, maybe a trig identity comes to mind. Okay, maybe u substitution comes to mind because we've got well, that's for derivatives. U substitution would be the process for integration. So maybe you're thinking about something like that, but then you start thinking, okay, well, what's the derivative of the inside? Well, that would be 2 tangent times secant squared. And that would have to be the du that we see outside. And I don't see that outside, and there's no way to really get it. Okay? But this is where what Terry said, if you happen to recognize 1 plus tangent squared equals secant squared, then we're in business, okay? Then it's the integral from 0 to pi over 4 of the square root of secant squared x. Okay? Well, the square root of squared is the first power, so this is now just the integral from 0 to pi over 4 of the secant of x. Now we have something that we can take the integral of. And now we're actually able to, or once we do that, then we're able to use the fundamental theorem of calculus. Okay? So, the integral of secant is what?
Natural log of secant x plus tangent x.
Alright, natural log of absolute value of secant x plus tangent x. Okay? And we're going to evaluate that from 0 to pi over 4. Okay? Don't be surprised if this is on a portion that you can't use a calculator for, because this is all unit circle. So let's work it through here. First thing, I'm going to have the ln of absolute value of secant of pi over 4 plus tangent of pi over 4 minus the natural log of the absolute value of secant of 0 plus tangent of 0. Okay? Not theta. 0. Okay? So let's figure this out. Secant's 1 over cosine, right? What's cosine of pi over 4? Square root of 2 over 2. So secant is going to be the reciprocal of that, right? Yeah, that's 2 over the square root of 2. What's tangent of pi over 4? 1. Alright? Okay, so minus ln of, what's cosine of 0? 1. So secant of 0 is 1. What's tangent of 0?
0.
Okay. So notice what we've got here. We have the natural log of 2 over root 2 is the same thing as square root of 2. So it's just a square root of 2 plus 1 minus, what's the natural log of 1?
0.
It's 0. Okay? That's all 0. So right here, this is our final result. Okay? ln of square root of 2 plus 1. Alright? One last application. Alright? One last application is average value. We have our mean value theorem, okay? That helps us find average value. So if I want the average value of tangent from 0 to pi over 4, I'm simply taking 1 over b minus a. So 1 over pi over 4 minus 0 of the integral from 0 to pi over 4 of tangent. What's the integral of tangent? That's the other way around. That's derivative. What's the integral of tangent?
Integral of tangent is negative
Oh, wait,
natural log of
that's-
cosine.
What?
Negative natural log of cosine.
Negative natural log of the absolute value of cosine. So 1 over pi over 4 times negative natural log of the absolute value of cosine. And we're going to evaluate that from 0 to pi over 4. So, we figured this out here. 1 over pi over 4 is 4 over pi. We have negative ln of, what's cosine of pi over 4? Huh? Root 2 over 2. Minus negative ln of, what's cosine of 0? 1. Okay. So what's ln of 1? It's still 0. Okay.
Wait, where'd you get the other negative from?
Because I'm doing fundamental theorem of calculus, it's f of b minus f of a.
Oh, I didn't see the.
And then the integral itself had a negative in it too. Okay? Alright, so here we get to our answer, 4 over pi times a negative, so negative 4 over pi, ln of the square root of 2 over 2.
So the answer is a positive number or
Well, the natural log, well, root 2 over 2, root 2 over 2 is actually like 0.707, which is smaller than e, right?
so it will be negative.
So you know that natural log is going to be negative times a negative is going to give you a positive value in the end. So our average value here is going to be positive. Now, can we simplify this more? Yes. Okay? Are we going to want to unless we're told we have to? No. Okay? But just to kind of show you where you can go with this. Okay? So, I could, if I wanted to, bring the negative in as an exponent, right? I could make it negative 1 power. Alright, so I could rewrite this as 4 over pi times the ln of root 2 over 2 to the negative 1, which is 2 over the square root of 2. And what does that equal? Square root of 2. So I could rewrite it like this. Okay?
Oh, you're doing like 2 to the negative 1 power too.
Well, I did that whole thing. I brought this in as a negative 1 power.
Oh, so that goes to the bottom.
So yeah, you flip it, and 2 divided by root 2 is root 2.
Oh, because you said like the coefficient of the log is the exponent. Okay.
Exactly. Do I have to do this? No. I'm just showing you what you can. I could even bring the 4 in. And I would have, if I took the 4 in, I'd have 1 over pi still left on the outside. And I'd have ln of the square root of 2 to the 4th power. Well, square root of 2 to the 4th power is 4. Okay? That's a square root of 16, so it's just 4. So, this answer that we got originally is perfectly acceptable. Stop there. Unless you're told to keep going. Alright, maybe you're told, hey, show that the integral equals 1 over pi ln to the 4th. Or maybe it's a multiple choice. And you get to here and none of the answers match. Okay? You may have to do some extra simplifying to see if your answer does match one of the choices. In which case you could keep going all the way down to here. Okay? So, just some thoughts there related to simplifying, but notice we're doing many of the same things, same applications that we did with all of our other integrals. We just now have a couple more properties or a couple more rules so that we can do some different functions than we were able to do before. Okay? All right.